Hello everyone. Today we are going to find the area under a curve using a slightly different approach than last class. We are going to be using rectangles instead of trapezoids, which may seem like a downgrade in terms of precision if you look at the diagram on the right here, but if we use sufficiently many rectangles, you'll see this is not a problem at all and actually seems to be a little more elegant than the trapezoid method. So remember, we're trying to find the area under a curve from A to B between the curve and the x-axis. So what we're going to try to do today is find the area under this particular curve from 2 to 5. So before we get into the weeds with this problem, it would be nice to take a quick look at what it is we're actually trying to do. Well, good news, the future is now, and there is a tool available on the World Wide Web that allows us to play around with this. There's a link in the description. Sticking with that theme, I've paired this next segment with some very futuristic sounding and more importantly free music. So if you feel the calling, I'm sure nobody would get overly upset if you decided to nod your head or dance a little in your chair. Ready? Here we go. And we're back. So hopefully you can see what the goal is now. We're going to work off of this diagram a little bit to determine a general form for the area under any positive curve on an interval from A to B. So the width of each of these rectangles we can call delta x, and the heights would be determined by f at A, f at x1, f at x2, and so on. We could also call f at x1 f at A plus delta x. We could call f at x2 f at A plus 2 delta x, and so on. So we're going to determine an expression for the area of some rectangle touching the curve and the x-axis. So the area of the ith rectangle is base times height. The base for any rectangle is going to be delta x, and the height of any rectangle is going to be f at xi. So I changes depending on which rectangle we're looking at. So now we need to sum the rectangles of the same width, and we can use sigma notation. So the area under the curve using n rectangles is going to be given by delta x f at xi, and we're going to iterate I from 1 to n. So delta x, if we're going from an interval from A to B, this full distance is B minus A. And then if we're splitting that up equally into n rectangles, the width of each rectangle will be given by this. And f at xi, we could also say is f at A plus I delta x. Or if we put this in for delta x, we can say this is also equal to f at A plus I b minus A over n. So we should note the larger the number of rectangles within the interval, the smaller the width of each rectangle. So if we make the number of rectangles infinitely large, so n approaches infinity, then the width will get very, very small, and we will have an exact value for the area under the curve. So we can sum the areas of an infinite number of rectangles of infinitely small width. So we have this, where delta x equals b minus a over n, and f at xi equals f at A plus I b minus A over n. So we have this roughly on our formula sheet. Delta x times f at xi summed from 1 to n as n approaches infinity. Delta x is given by b minus A over n, and f at xi is f at A plus I b minus A over n. So now we're in a position to finally find the area under this curve from 2 to 5. So we're going to start with our expression above. A equals limit n approaches infinity delta x f at xi. going from 1 to infinity. So next we're going to have limit as n approaches infinity. Delta x we can put 5 minus 2 over n, so that's b minus a over n. Then we have f at a, which is 2, plus I times b minus a over n. And this will become just 3 over n. Same thing here. So next up we'll have 3 over n, and we can sub this in for f of x here. So everywhere we see an x, we're going to put this in its place. So we're going to have 2 plus 3i over n squared minus 2 plus 3i over n plus 3. So we have 3 over n, 4 plus 12i over n plus 9i squared over n squared minus 2 minus 3i over n plus 3. And we can simplify this a little bit now. So we still have 3 over n, 9i squared over n squared plus 9i over n plus 5. So next we're going to go 3 limit n approaches infinity, sum, and we're going to go ahead and distribute this n into everything. So we will have 9i squared over n cubed plus 9i over n squared plus 5 over n. So we can apply this sigma to each one of these terms separately, which will give us sum of 9i squared over n cubed plus sum of 9i over n squared plus sum of 5 over n. So we can use a few of the partial sums developed from last class. For the I squared, it's n times n plus 1 times 2n plus 1 over 6, and that's from 1 to n. And for the sum of I from 1 to n, we can replace that with n times n plus 1 over 2. So next we will have 3 limit n approaches infinity, and this first term using the partial sum will become 9n, n plus 1, 2n plus 1 over 6n cubed. The second term here, using this partial sum, will become 9n times n plus 1 over 2n. And this sum, using the property we developed last class, if we have a constant in here and we're going from 1 to n, this becomes n times c. So 5 over n is a constant, and we would put that in place for c. So we would have to do 5 over n times n, which would just give us 5. So 5 goes there. So now we can simplify this a little bit. 9 over 6 reduces to 3 over 2. 1 factor of n cancels there. 1 factor of n cancels there. So next we'll have 3 limit as n approaches infinity of 3 2n squared plus 3n plus 1, just expanding that expression here, over 2n squared plus 9n plus 9 all over 2n plus 5. So next we're going to have 3 limit n approaches infinity, and we're going to bring each of these terms over top of 2n squared. So first 3 times 2n squared is 6n squared. 6n squared over 2n squared is 3. Then 3 times 3n is 9n over 2n squared. That becomes 9 over 2n. And then 3 times 3 over 2n squared becomes 3 over 2n squared. This 9n over 2n would just become 9 over 2 because the n's would cancel. The next term would be 9 over 2n, and last we would have 5. So in the limit that n approaches infinity, each one of these terms would go to 0, and we would just be left with these 3 numbers in the brackets. So finally we would end up with 3 and then 8 plus 9 halves. So 8 plus 9 halves would give us 25 halves. And we can simplify that further to 75 over 2, which would approximately be about 37.5 units squared. So that's it for me for today. I would encourage you to try these questions out in your textbook, and I'll see you next time.